Welcome to Lecture 9 of the CS4423 networks. My name is Götz Pfeiffer, and this video, is about closeness and betweenness centrality. So, in addition to the two centrality measures that we've already seen, the degree centrality and the eigenvector centrality, we're going to study two more centrality measures, which again are different in their ways. Closeness centrality and betweenness centrality. We study them on the same graph, the marital tie graph of the Florentine families, and that allows us to compare these centrality measures with each other. As usual, we start by importing the packages we need, networks, pandas, and a queue for a further application of breadth first search. So let's recover the graph G and the data that we already compiled from the file where we left it last time. To remind you, that's the graph we're working with. And we had associated to each node the two centrality measures and the degree itself. For example, the Medici node in the network now has attributes CID, CIE, a degree attribute, and real-world attributes counting the number of priorats as it in seats on the city council and their wealth in some currency. And we have a graph that consists of 16 nodes in total. Right, closeness centrality. Here, a node X in a network is regarded as being important, being central, if it is close to many other nodes, as it then is in a position to quickly interact with them, to quickly exchange messages or whatever the purpose of the network is. A simple way, in terms of formulas, how to measure this closeness can be based on the sum of all the distances to all the nodes in the network or in the connected component. So this is closeness centrality, which applies to a simple connected graph. Connected meaning there is a path between any pair of vertices. And then we can define the closeness centrality as the reciprocal of the sum of all the distances of the other nodes, or of all the nodes to the node I in question. There's no need to exclude node I itself, because that would have distance 0 from itself and doesn't change the sum here. The point is we're inverting things, so this sum must not be 0. That's why we need a connected graph. Then in order to move this centrality measure into the range of values between 0 and 1, we multiply the closeness centrality defined in this way by n minus 1. That's the number of other nodes, and that is then the normalized closeness centrality. How do you compute closeness centrality? Well, you've guessed it, it's by breadth first search. It was said earlier that we can use the notion of distance and the breadth first search as it determines it between all pairs of nodes to find exactly these distances dij that are needed in the definition of the closeness centrality. So we can use what we prepared not too long ago, breadth first search, this time a bit adjusted to the environment we're working in. So because we're going to use this repeatedly, we wrap the strategy up into a Python function, call it distances. So it takes a graph and a node, a vertex x of that graph as its arguments, and then it runs through the breadth first search as we know it, computing the distances of all nodes y in the graph to the given node x. That's the algorithm as we've seen it before. The only difference here is that the list of distances is no longer called D but dists, and it is a Python dictionary rather than a list, which assigns to each node y in the graph initially none and eventually its distance to x, to the x node. So apart from that, the algorithm is the same. We set up a queue, initialize the queue with the given x vertex only, and then we keep looping over the queue, popping new elements y off the queue. Then we inspect all the neighbors of that current y element, check whether we've seen it before, check whether the distance entry at z is none, as we did before. If it is none, if it is unseen, we compute its distance as one more than the distance from the current y node that we popped off here, and we push the z node at the end of the queue. And at the end, step number 3, we return this dictionary of distances. To see how this works, let's define this function and apply it to the Medici node. Compute all the distances in the graph from the Medici node. And if we print this, you see this is a dictionary. It's a list of key value pairs where the keys are the nodes, the family names, and the values are the distances from the Medici node. Now we have here all these A families on Acciaioli and Albizzi Barbadori at distance 1. That should be, that's what the graph says. The direct neighbors, there's one Tornabuoni, distance 1, where there Tornabuoni is distance 1. And all that is recorded in this distances dictionary. One is sticking out. The isolated node, Pucci, has no distance at all. It hasn't been reached. It's not part of the connected component. And if we look at this whole game from the perspective of the Pucci node, you'll see it has undefined distances to all the nodes in the network, except to itself, where it has distance 0. So the sum of the recognized distances here would be 0, and inverting that would be a division by 0 error. This is only asking for trouble. So from now on we exclude the Pucci node from the graph. We remove this node from the graph and update the n counter of number of nodes accordingly down to 15. Now we're looking at a connected component, a connected graph only. In this graph, we can now compute the distances function that we provided, the version of breadth first search, to compute all the distances between all the nodes and add them up as required in the definition. So for a given node I, we find all the distances of all the nodes to I, add them all up, invert it, and multiply it with n minus 1. That's something that can be based on the distances function. Now we list for all nodes x in the graph, we list all the distances of the other nodes to the x node. Take the values in this dictionary, add them all up, and multiply that or divide this into n minus 1. That's the definition of the normalized closeness um, centrality for all the nodes. And we get it in the form of a dictionary, which has for every family in the network an associated distance, closeness centrality, computed in this way, computed according to the formula in the definition. Of course, the networks has its own function for that, and it's called closeness underscore centrality. If we apply this to the G graph, we get a similar data structure, a dictionary that has for every family name an associated value, and in fact, if you compare them, it's exactly the same. So that's how it works. That's how even the networks function works. And you can actually use the Python equals operator to compare these two dictionaries, and Python reports back true. They're exactly equal. So we can add these measurements to the table as we did before. Add a new column, capital CIC, this superscript C for closeness centrality, and use the nice features of the pandas data frame to display the new table. Okay, the order of the columns has changed a bit from last time, but never mind, right? This is still nice. And here's the new column, the closeness centrality, and now one can see similar to what we noticed before. So the table here is still sorted by the degree in ascending order, and the closeness the rank that goes as the closeness centrality is roughly the same, but not entirely. Here's a closeness centrality. The Ridolfi have a closeness centrality of 0.5, which in that ranking puts them on place 2, doesn't it? Just after the Medici, and here they're like in the middle. Let's check the Ridolfis in the graph. Can we see the graph? Where are they? Here, yeah, I don't know, how would you describe it? They only have 3 neighbors, so that's a small degree in comparison, but somehow they sit right in the middle, not too far away from everybody. That's what the closeness centrality measures and then reports. They're important in terms of closeness. Okay, second measurement on the list is the betweenness centrality. This is based on possible interactions between agents on a network, nodes regarded as agents in a network, and interactions communicated through the links of the network, whatever they represent, like people know each other, people have their children married to each other, or transport opportunities between here and there, whatever. The network's perspective is an abstract one. We only deal with vertices and edges between them. And so if nodes are agents that interact, and these interactions have to travel along the paths between those nodes, then they do depend on the nodes in between, on these middlemen. In particular, if these middlemen sit on shortest paths, which would be preferable for such interactions, to make them most efficient, I suppose. You choose a short path to interact with your business partner, possibly, ideally, a shortest path. Through this natural way of things panning out, and the power comes to those in the middle. Betweenness centrality measures centrality in terms of shortest paths that pass path through a node. That shortest paths pass through a node. So it's a somewhat complex thing. It's one added layer of complexity to what we've seen before, because now we're not only measuring distances between a given node and all the other nodes to determine a measurement for that node. We look at a particular node I here, and then in relation to a given node I, we look at all pairs jk of nodes, and then look at all shortest paths between j and k, and try and determine amongst them the proportion that passes through I. And that, added up in a suitable way, measures the betweenness importance, the betweenness centrality of the I node. As it says here, in a simple connected graph, the betweenness centrality, CIB, B for betweenness, of a node I is defined as a double sum, a sum over all j and over all k, and both j and k are supposed to be different from the I node itself. It's about being between, not being equal to an end point. And then, given j and k, there are shortest paths between j and k. We count them and this number we call njk. That's the number of shortest paths from j to k. And njk of I denotes, out of those, the shortest paths that have the node I on it. Then the normalized betweenness centrality the normalized betweenness centrality is obtained by dividing this number by n-1, n-2. This is then a measurement that takes values again in the interval between 0 and 1. It makes it convenient to compare these measurements across different networks. n-1, n-2, if you think about it, is the largest number of shortest paths a given node can possibly lie on. There's the node itself, and then you have, which must be different from the endpoints of the short path. And then you pick one endpoint, you have n-1 choices for that, and then to be a path, again it must pass, and passing through, it must be a distinct node again. So you only have n-2 choices for that. That gives n-1, n-2 possible shortest paths at most that the I node could be sitting on. And again, question, how do you compute this in a given graph? How you determine this measurement? Answer, breadth first search. So we'll try to do something similar to what we did before. We use breadth first search to compute a dictionary that assigns to each family name the closeness centrality. Now we need this betweenness. We need to determine these shortest paths in some systematic fashion. And one way to do this, and in some sense we've done this before already, is to use the breadth first search to compute, while you're finding the distances, to compute also a list that contains for each node its immediate predecessors on this list, in this search. So again, you're given a graph and a vertex x of this graph, and We've just used breadth first search to compute for every node y in the graph its distance from the x node by systematically traversing the graph. And while we do this, we now want to record all the other vertices that could be immediate predecessors on the shortest path from the given x node to the current y node. And we've already seen how this works. That we've already seen that this information is there. It's something that breadth first search can pick up on the fly when we constructed a spanning tree the other day while traversing the graph. We remembered whenever we found a new node, a node that we hadn't seen before, we remembered the edge that brought us there. And by remembering the edge, you remember one immediate predecessor of this node on the shortest path leading back to the x node, and to the root of the graph as we have it now. And here, instead of only one predecessor, we want to find them all. And it turns out that since you have to, with the breadth first search, you have to look at all the edges anyway to make sure they don't give you a new node. And if they don't give you a new node, you might discover at that time that the edge comes from another possible predecessor, and that can be recorded. So, long story short, the algorithm we had to find all the distances only needs to be modified in a few small places to find the list of immediate predecessors. And the way we do this is working from the previous Python program. Instead of one dictionary which lists the distances, we set up two dictionaries, one for the distances and one for these lists of predecessors. Distances are initially set to none, as before, and the predecessor lists are initially empty lists for every node in the graph. And then we'll do our breadth first search, set up the queue, loop over the queue, inspect the neighbors, inspect the edges leading out of the current node y that we popped off the queue. If the neighbor z hasn't seen before, it's a new one, then we know its distance from the x node is one more than the distance of the y node. And now we also record the fact that this y node is a predecessor of the z node. And then in that case we push the z node back. We push the z node at the end of the queue as a new thing to be looked at later. And if the z node has been seen already, then still this time we arrived there through a different edge, and we need to check whether this edge could be part of a shortest path leading to the z node. And this can be checked by making sure that the distance, which at some point when we discovered the z node, we recorded in there, the z distance is bigger than the y distance, the node that we're currently coming from. Then again, this y node could have been a predecessor or the shortest path, and we record this by adding the y node to z's list of predecessors. So that's a 1, 2, 3, 4 line modification of the breadth first search we used for the distance. So define this and let's see this in action. I find it always helps to have an example. So let's traverse the graph starting from the Medici node, that's the root node then, and then compute the predecessors as we go along. I will find that the Medici themselves have no predecessors in this search, because they're the root. Yeah? That's where all short paths start. Then what else? There's lots of nodes which have just the Medici node as a predecessor, and that's 1, 2, 3, 4, 5, 6. Yeah, that's the 6 immediate neighbors of the Medicis. There's the shortest paths from a Medici from there to a direct neighbor is that edge, full stop. That's why these have only one immediate predecessor. But there's a few longer lists, like the Bischieri have Guadagni and Strozzi as immediate predecessors. And that's expressing the fact that, as you see here, from the Medici to the Bischieri node, you can travel along a path of length 3 this way around or that way around. For the graph, it doesn't make a difference, and the two immediate predecessors on these two distinct paths of length 3 are the Strozzi and the Guadagni. That's what the algorithm discovered. And similar for the other longer lists. And then, okay, that's something, that's another thing the breadth first search can do for us. And what are these lists good for? Well, we can, using knowing the predecessors, then we can recursively make all the shortest paths in a systematic fashion. Well, that's if we know all the predecessors, then with respect to a root node x, then the shortest paths from x to y can be enumerated recursively. If y is the same as the root node, we saw that, then the shortest paths, the only shortest path from x to itself is the empty path, ending and starting there at x itself. Otherwise, if y is different from x, then each shortest path from x to y travels eventually to y, and on that way, in the penultimate step, it travels through one of its predecessors, and then it ends in y. So a shortest path from x to y consists of a shortest path from x to a predecessor, say z of y, plus the edge that connects z to y. Or in formulas, if you prefer that, calling s subscript x of y the set of shortest paths from x to y. The set of shortest paths from x to itself is just the empty path, the single vertex list x, and then recursively the set of shortest paths with respect to x of y can be described as the set of all paths of the form p extended by y, where p is the shortest path from x to z, and z is an immediate predecessor of y with respect to x. This formula, I wrote this down because it helps me to translate this description in words into a working program. Like this, shortest paths, parameters x, y, and then the predecessor's dictionary that we computed earlier with the breadth first search, implementing exactly what it says here. If x is equal to y, then we return a list that consists of x only. Otherwise, we can accumulate in a growing list paths, these things here, looping over all predecessors z of y with respect to x, and that's stored here in the pre-dictionary, and then an inner loop over all the paths in the set of shortest paths from x to z that's computed recursively here. We And we use Python's plus to concatenate these two lists to form a new path, which we append to the growing list paths that we then can return at the end. Or if you prefer Python's list constructor, the Python list comprehension with for loops, with two for loops on the inside. I think that does the same trick, and well, whatever is clearer. And so so now I have in a variable p, I have the predecessors. P I call this. I have the predecessors dictionary of the G graph with respect to the Medici node. And from there I can find all the shortest paths from the Medici to the Bischieri. And the program lists 3 of them. Passing through Albizzi, Guadagnini, Bischieri, or Tornabuoni, Guadagnini, Bischieri, or Ridolfi, Strozzi, Bischieri. Oh, 3, I didn't see that before. Here, Medici, Albizzi, Guadagnini. Oh yeah, there's a third short path from the Medici to Bischieri. Now path of length 3 of them. Alright, so yeah, that's the machinery in place. Now we can list all the shortest paths between all pairs of nodes systematically. And so we can now move on to compute the betweenness, starting with a dictionary that has for each node x in the graph a value of 0. And then we loop over all the graphs. What did I do wrong now? We loop over all the graphs. Betweenness is not defined. This first. Then we loop over all the vertices in the graph G. With respect to that vertex x, we compute the predecessors using the breadth first search from earlier. And then again an inner loop for over all vertices y in G. And we've determined that list of all shortest paths from x to y, as we did before. And all we're interested in here now is how many are there. That's given by the length of this paths list, which we immediately normalize by multiplying it by n-1 and n-2, n being the 15 from earlier. That's and that's the njk value. Now the number of shortest paths from j to k, okay, normalized since we're multiplying it with n-1 and n-2. And then for to find the ones that are passing through the x node. No, to find the ones that are passing through, to find, we change the point of view. We start with the path and then find all the nodes on the path, all the nodes z on the path that this path passes through. So this path adds njk to a node z's betweenness centrality, or 1 over njk. That's how we do it. Now we loop over all the paths, then we loop over all the nodes on the path, excluding the end points, and add 1 over njk to that node z's betweenness centrality. It gives a dictionary of values, as before, 1 value for each family. There's a few at 0. Why is that? I'll ask you to find this, to find a reason for that. And of course the networks has its own function for this. It's called betweenness centrality, and it gives a dictionary that assigns to each family name a value. If you compare the numbers, they're more or less the same, except for tiny differences here in the final digits, and they're not exactly the same as the equals operator reports, but they're morally the same. Who needs 20 digits accuracy here? So that's the betweenness centrality for this graph. Albizzi, no, wasn't it? The first one's Acciaioli 0. Oh yeah, they're here, the leaf node. How can they be between things on shortest paths? That's why they're 0. So now we can add these newly calculated attributes to the table, print out the table one more time, and now same as before, the new centralities do roughly correspond to the order in which we do print this list all the time, namely the degrees, or the degree centrality. Looking at the values, okay, we found the zeros, and I think we saw an explanation for the 0. Some values are a bit out, and this is very small, 0.02. This one is very big in comparison, I'd say. 0.52, and the next one up is 0.25. Now the Medici have a betweenness centrality which is more than twice as much than the nearest competitor. That's a drastic difference. That's a big difference, and maybe that's the reason why their name is still the one of these 15 that is remembered now, more than 600 years later. Anyway, that's the centrality. That's 4 different centrality measures that can be performed on a network, measuring different ways to be important. We've seen that as a node on a network, you can be important if you have many friends, that's measured by the degree centrality, or if you have important friends, that's measured by the eigenvalue centrality, or if you are close to many, that's the closeness centrality, or if many interactions pass through you as a node, that's the betweenness centrality. And that's it for now.